you could go to the Menti poll. We like to do this at the beginning of all of our webinars to get a sense of the makeup of our community that we're trying to build here. This is the first question, and just trying to get a sense of the career stage of our participants. The next question is more fun. Do you see the waiting room, Heather? For those of you just joining, there's a Menti poll. You can join using the code listed there, or if you're on a smartphone, you can scan the QR code. We've got 8 responses, but we've got 14 participants. So can anybody who hasn't yet please fill in the Menti?
I don't see where to fill it in, actually. Where do you fill it in?
You just join. So you go to menti.com in your browser and then just enter that code and it'll bring up this poll and you can submit your answers through the poll.
So Heather, with this new setup, will people be able to unmute themselves at the end to ask questions, or would you need people to ask questions in the chat?
We might have to use the chat. This is set up as a webinar instead of a meeting. So I'm not certain what participant functions are enabled for this. They might be able to unmute or raise hand and then we can unmute them.
Oh yeah, okay, I see. If they raise, we can allow someone to talk.
Yeah.
Okay.
We really had to button it down after an unfortunate.
I heard.
It was awful.
Yeah.
Okay, I am going to move to the next question because it's a fun one. The next question is, please tell us what deltaic systems you are working in or have worked in. And I apologize, I'm not sure if I set this up for to enter multiple responses. So if it only lets you enter one, just tell us what one you worked in most recently. Go, Florida. Pretty good global coverage here.
Oh, this is cool.
Looking good, everybody. Wow, we have probably 20 to 25 participants, but that's pretty good, a global span there for not a huge group of people. All right, well, I will leave this up while Julia gives the introduction, and then we can switch it over to Bob so he can give this fantastic talk. Thanks, everybody.
Okay, can you hear me?
Mm-hmm.
Okay. Great. Well, welcome everyone to the Leaky Deltas seminar. I hope everyone is having a good morning or evening or whatever part of the day you're in, wherever you are in the globe. And so today I'd like to welcome Bob Aller. He's a distinguished professor at Stony Brook University School of Marine Atmospheric Sciences. He got his PhD at Yale University and since has gone on to have a very distinguished career. He works on early diagenetic reactions in elemental cycling involving the decomposition of organic matter, dissolution of inorganic biogenic debris, and the mobilization and reprecipitation of metals sensitive to redox reactions. Bob has worked in a variety of coastal and deep sea marine areas, including Long Island Sound, French Guiana, and Papua New Guinea. And with that, I will turn it over to Bob, who I think is going to share his screen. And thank you everyone for bearing with us while we work with the new tech setup. But we'll unmute people we think we can unmute people at the end to ask questions. Or you can put questions in the chat at the end. And I'll keep an eye on the chat during the presentation. And so now I'll actually turn it over to Bob, who will be talking about shoreward transport and deltaic systems, the coastal vacuum and reactive particle processing.
Okay. I'm trying to change my view here a little bit.
No rush.
Oh my. Okay. Can you see my screen okay, Julia?
Yeah, I can see your screen great. I
You
have no
see all the
problems.
participants too? That's what I'm seeing.
Oh, I see all the participants on the right-hand side, but your screen is the main thing that I see.
Okay, super. I can go because it's just an annoyance to me and not really critical. So I'm gonna talk about coastal systems associated with deltaic regions of the ocean, and in particular, I want to emphasize the exchange of material with the coastal ocean and outer ocean regions, and something that I referred to in this particular title as a coastal vacuum. So let's see, here we go. What is going on? Okay, so I first want to acknowledge all the different people that I've worked with on this, and up front indicate that there's lots more people than myself involved with everything I've talked about. And of course, like many of us, I'm highly dependent on the participation of all of them and the interactions with all of them. Now, one of the things I wanted to start with was to say that the way we address a lot of deltaic problems and the interactions of deltas with the oceans is to view them often as a unidirectional transfer of material from the continents to the oceans. And it's sort of built into the conceptualization of inshore patterns to offshore patterns. And we get, we have, let's see if I can get a laser here. We have arrows like this, which are almost inevitably unidirectional, indicating material transfer from one region to another along a progressive pattern, going from the land into the interior ocean. And I'm going to talk about two such areas today, the Amazon and an area in Papua New Guinea, which you'll see a bit later, called the Gulf of Papua. And I'll explain these different areas and regions and what they represent. The numbers on these maps if you aren't familiar with them, refer to the millions of metric tons of sediment introduced from the different drainage basins shown. And these are in fact contrasting drainage basins, low yield regions like the low gradient regions like the Amazon, and high gradient regions, which I'll talk about later, like Papua New Guinea. Now, along the sort of idea I've been talking about is one of the ways we look at these kinds of processes associated with deltas and inshore, offshore patterns is to look at patterns like this as a function of bathymetric depth here. And in this particular case, it shows net sediment accumulation rate as a function of bathymetry here, and moving from the shoreline into the deep sea. And here is a logarithmic diagram that you can see here. And there's a few deltas plotted here, and you can see immediately that the deltas have the highest sediment accumulation rates, and they're also very, very variable, which is extremely important, as I'll talk about a bit later. But the main idea is that we're sort of, it's ingrained in the way we view things, that we're looking at material moving from this region progressively in this region. And what I want to emphasize today is these areas, these boundary areas that deltas represent, are highly interactive with the ocean, and there's a material transfer in both directions, not just from the land to the sea, but also from the sea into the deltaic systems. And one part of this transfer and movement of material is shown here. This is a plot from Paul Liu and others showing that many large river systems introduce material to the sea. A large quantity of that material accumulates immediately proximal to the river mouth, but also variable amounts of material move along shore. So we need to view these deltaic systems immediately as actually at least two-dimensional systems along the coastline, as well as at the proximal region of the delta. Since it's quite typical to get 20, 30, 40% or more of the material that rivers deliver to the ocean actually move along the coastline, and they don't accumulate in what we might refer to as the delta proper region. That's extremely important to realize. So I'm going to move now to talk about the Amazon system, which is one of my favorite systems. I've worked on it many decades, and I still work on parts of the system that are downdrift of the Amazon. This is the satellite, a real color satellite image of the Amazon mouth, which is at the equator here, which runs right along here. Here's the Atlantic Ocean. And what you can see is this sort of classic turbid plume emerging from the river mouth, moving into the ocean, and then a boundary just offshore where the turbidity begins to drop of green water, showing the incredibly high productivity that's associated with the input of the river material. So one of the things we know about these systems is, of course, they promote a lot of cross-shelf transport of nutrients from the river. Here's the Amazon mouth again. This is a CWIF's satellite image showing the annual average of primary production associated with the Amazon River inputs and delta system here to the ocean. You can see that it's not just right off the river, but rather all along the coastline. There's an enhancement of productivity, and then there's a what's called a retroflexion of the input of the Amazon plume into the interior Atlantic Ocean. But my point here is that it's ingrained that we're thinking of these systems as movement of material from the river into the ocean. But if you look more closely at some of these patterns of, for example, chlorophyll associated with the river mouth, here's the Amazon River mouth here. Here's that high turbidity water, which is pretty obvious here. Here's the green water showing you the very high productivity associated with this transition from high turbidity to lower turbidity water. And so there's extensive transport that's obvious, but you can see here these stringers of chlorophyll A rich water that are coming inshore. So we can already see on the surface of these images that there's a lot of shoreward transport of organic material produced in the ocean back toward the coastline. So I want to now talk more about the different characteristics of cross-shelf exchange, and not just the seaward transport, which I've been referring to here by the CWIFs type of satellite photo, but also the shoreward transport, which I was just showing an example of in terms of the eddy of chlorophyll A rich marine-derived organic matter shoreward toward the river. And I want to talk about some of the tools that we use and that illustrate some of these transport phenomena, particularly the shoreward components of transport. And I want to emphasize for the rest of the talk, radiochemical tracers, in particular lead-210 and thorium-234, and also a cosmogenic radionuclide that Shirley Raman has worked a lot on, and use an example there as well, showing the shoreward and alongshore entrainment of reactive biogenic debris to the coastline. And I'll give a couple examples of the seaward transport too, just to convince you that I'm aware of that as well, and that that's extremely important. But one of the things I want to get across here today is that if we want to understand carbon cycling in these coastal systems, in these deltaic systems, we need to view them in just that way, as systems that are associated with exchange in both directions. And there are a range of tools, not just carbon in and of itself, but there are a range of tools that we have available to us to quantify these exchange processes. So I'm going to go to a diagram here, which shows, again, the Amazon River mouth, but now the thickness of sediment that's accumulating off the Amazon River mouth that's characterized by extensive remobilization and reworking by the currents that occur on the shelf, including tides and wind-driven wave disturbance of the bottom. And this is the thickness, contour thickness of the lead-210 reworked layer that's seen off this river mouth here in over extensive areas. And now Steve Keel measured the thickness of this sediment mixed layer or lead-210 reworked layer extensively across the shelf, and it's defined by this kind of homogenization of the lead-210 profile. Here's the activity of lead-210 in the sediment in DPM per gram, and here's depth in centimeters depth. That's a characteristic profile that you might find for lead-210 in this region. And so this thickness shown here represents the reworked sediment as lead-210 sees it. And the gradient here right at the bottom of this pattern, the gradient in activity is what's used to back out the sedimentation rate in all of these sites. So you can see that getting the sedimentation rate in these systems using lead-210 can be actually tricky in and of itself. Now, one of the things I had mentioned this earlier when Christoph was giving his talk about the Rhone Delta and lead-210 is sometimes these lead-210 profiles, there's information in it that people just don't look at very often. They ignore them. They look only at a profile, a vertical profile, like I was just showing you. Here's depth here. Here's lead-210 activity in the sediment, again in DPM per gram. This is at a single station E1 on the Amazon topset. And you can see the thickness of this reworked layer is about 125 centimeters here, and there's a gradient at the bottom. And so what Keel and others did was look at multiple sites and looked at how the variability of this reworked layer changed seasonally. And so there's different times here, August, February, May, and October. And you might glance at this and see, well, the lead-210 mixed layer is about the same all the time. And so I can consider this system pretty stable as is. But if you go in to the in detail here and look at the actual lead-210 activities in the sediment, you'll see they're changing. For example, here you can see there are 3 dpm per gram at the interface. Here they're 2.5. Here they're less than 2. So even though this mixed layer thickness is remaining approximately the same as a function of time, actually the material at this site is completely exchanging in the upper 50 centimeters or so at least. So this material is moving back and forth from one place to another. So it's a highly dynamic system. And when you look at these radiochemical tracers, you need to view them not from the standpoint of a single profile. You need to actually sample multiple times at sites to be to constrain the sedimentary dynamics. Another tracer we use that actually also reflects this kind of disturbance and represents injection into the water column of benthic-derived solutes is radium, the different radium isotopes. And these show some beautiful data of radium in the bottom water of the Amazon Delta, the water overlying these kinds of sedimentary deposits I was just describing, showing you that seasonally there are huge differences, particularly in the radium-224 isotope in the bottom water, which is a 3.7-day half-life isotope produced in the bottom. And so what this is showing you is that there's tremendous injection into the bottom water of solutes produced on the shelf associated with this the sedimentary dynamics seasonally, and radium is reflecting this injection process seasonally. Now, one of the reasons I bring this up here is because associated with this injection of radium, here's radium shown here, is phosphate that's remineralized in the seabed. And so the radium patterns seasonally here, the fluxes of radium from the sediment, in particular 224, the very short life, half-life radium nuclide, is showing you that there's a tremendous injection and recycling of benthic nutrients into the bottom waters here on the shelf. Now, it's not just injection into the bottom water, it's also movement of bottom water onto the shelf from offshore. And this is shown here, again, using lead-210, but now rather than the gradients in lead-210 or the vertical patterns of lead-210 in terms of activity, you can use inventory, the total amount of lead-210, excess lead-210 in the sediments. And this represents some really fantastic work headed by Dave DeMaster many years ago, showing that in these systems, in these deltaic systems like the Amazon, you can use the amount of lead-210 inventory in the sediment to give you a sense of how much exchange of water there must be shoreward in this system that is time integrated by the lead-210 signal in the bottom. So now I'm switching to talking about the amount of lead-210 in the deposit. And what you can see is this inventory here, which is the total amount of lead-210 in the sediment in dpm per centimeter squared of bottom area is shown here. You can see these contours showing you massive amounts of lead-210 that is clearly has its origin offshore, and the lead-210 is moving onshore up in upwelled water and being extracted in that highly turbid water, which you saw earlier, by the particles that are resuspended from the bottom, and they move shoreward. So there's a lowering of lead-210 inventory. Now, the amount of lead-210 inventory that you'd expect based on the atmospheric inputs of lead-210 to this region are just of the order of 10 dpm per centimeter squared or so. And so there's a couple of things I want you to notice here. One is that the surface activity of lead-210, despite the fact that there's a huge supply of lead-210 here from offshore that's being upwelled onto the shelf and moving across the shelf, that the activity of lead-210 in the surface, shown here in dpm per gram, is pretty homogeneous across the shelf. In other words, the surface material here is moving back and forth with tidal excursions of the bottom water and being homogenized. But the amount of lead-210 that's actually building up in the sediment is quite different from place to place, as the inventory varies substantially. So the lead-210 is upwelled from bottom water here, moves onto the shelf, is scavenged, accumulates in the bottom, and we have a record then of the total amount of lead-210 that's upwelled. And what DeMaster and co-workers did was relate that upwelled water to the onshore nutrient flux, and were able to show that, one, the volume of water upwell is about 5 to 10 times the Amazon River flow, and that it supplies 40 to 80% of the nitrogen that's needed on the shelf by phytoplankton activity, about 50% of the phosphorus, and about 20% of the silica. So this is a record stored in the bottom of the integrated onshore movement of water that's now processed, that now stimulates primary production, the products of which also move shoreward as they fall into the bottom water and are entrained into those mobile bed regions that I mentioned earlier. So about 5 to 10 times the Amazon River flow is moved onshore, as shown by this tracer. Now I want to talk more about what happens to the material downstream as it moves from the Amazon River mouth along the coastline, which it does in a series of what are called mud banks, essentially deposits of mud that look like this in a particular site. You can see a mud bank complex here. They're about 60 to 80 kilometers long and about 30 kilometers across, moving into the ocean. And they're flooded with water tidally twice a day with a couple of meters of water depth. Here you can see the mud deposits are exposed subaerially here. And so this is one such mud bank complex. And this is a highly dynamic coastline. This is actually a figure showing the position of the coastline as a function of decade here, 1950, 1975, and 2010. And the oscillations of the coastline and the migrations of mud banks along it are associated with multi-decadal forcing. So a lot of the coastal interactions I'm talking about today have longer term frequencies associated with the patterns of exchange that occur along them. And so you should be aware that there are decadal, in this particular case, decadal variations in a lot of these processes I'm referring to. And this is one of those exposed mud banks here. So this is a blow up of part of a mud bank along the French Guiana coast, and the scale here for it. Now, I just want to say a few more words about mud banks before I get to another system here, which will be the Gulf of Papua, because these represent what's important to realize is that the entrainment of water offshore does not just stop at the delta, proximal delta regions of the Amazon, but actually extend all along the coastline as these mud waves move and migrate along the coastline. And so we have mobile mud here. We have mud that's stabilized for different periods of time, as you'll see in a moment here, as shown by lead-210. So here's a mud bank just migrating from the Amazon downstream toward along French Guiana toward the Orinoco River. Now, these are characteristic types of profiles of thorium-234 and lead-210 that you find in these mud banks. And one of the things I want you to realize right away is it is absolutely remarkable that you find any excess thorium-234 in this mud. Thorium-234 has a 24-day half-life. It's produced by uranium in the water column, ocean associated with salinity in the ocean. And so you need water, you need seawater to produce thorium-234 that can be extracted into the seabed. And the fact that we see, I'm trying to drag all these pictures I have of myself and other people someplace else. Sorry. There we go. That's better. Now you can see this is the inventory of thorium-234 in one of these mud banks. It's showing you get 3 to 9 DPM per centimeter squared. And let me tell you that if you have about 10 meters of water depth, every centimeter squared for a typical salinity, open ocean salinity of water depth, you'd expect about 2.8 DPM per centimeter squared inventory. So now we just have a couple of meters just for part of the day of water here that could produce thorium-234. And in fact, we get 3 to 9 DPM per centimeter squared. So the bottom line is that there's a lot more thorium stored in these mud banks that could ever be produced by the water anywhere close to those mud banks. And this is showing you that particles are being advected shoreward toward the mud banks. They're not just moving along the shoreline with the mud banks, but they're being entrained in the mud banks from offshore. And here's lead-210, showing you homogenized lead-210. So this shows you what I'm talking about. Here's the water column, thorium-234 being produced in the water column in proportion to the amount of uranium-238. The water depth determines the underlying inventory, coupled with the salinity of the overlying water. So what's happening in these systems is that the thorium-234 produced in deeper water offshore is being advected with particles to the inshore regions and accumulating an inventory inshore that's far greater than you would expect based just on the overlying water. So this is one of these tracers we have of reactive particles. Now I'm going to show you something from Long Island Sound, which is different, obviously, than the Amazon. But this shows you that the amount of remineralized ammonium in sediments of Long Island Sound tracks very closely the excess thorium inventory in the bottom sediments that you see there. And this is typical of essentially everywhere. The thorium-234 associates with reactive particles. And so where we see thorium-234 excess in the bottom sediments, we inevitably see excess reactive carbon coming in. So back to the mud banks, back to lead-210. The outer part of a mud bank is high in lead-210. The inner part of mud banks is low because it's stabilized for a half-life or so of lead-210. So the activity of lead-210 in the inner part of a mud bank has decayed away by about time scale of about 30 years or so as it's stabilized. It will be remobilized and reemerge into the outer mud bank and migrate down the system as mud moves from the Amazon to the Orinoco. Now, another indicator of this entrainment of reactive particles from offshore is the remineralization of organic matter in the sediments of mud banks. And this shows you the stoichiometric relationship of dissolved ammonium in the pore water with dissolved DIC in the pore water. And the ratio that we typically see in these mud banks is very close to the Redfield ratio, showing you that marine organic matter is being entrained into this mud all along the way as it moves from the head of the Amazon River to the Orinoco. Now, this is a schematic diagram of this system that I like to show, showing you the Amazon River here, the Orinoco River here. Mud is accumulating proximally here off the Amazon River, creating those thick mixed layers you saw earlier, and part of it's migrating in these mud banks along shore. And I want to emphasize that not only do we get as shown by those CWIFS images and those chlorophyll A color bands, seaward exchange of material. But as the lead-210 and thorium-234 shows, you get shoreward exchange of the highly productive, highly reactive particles produced in the highly productive regions offshore coming back onto shore. Now, we can quantify some of these entrainment here, and this is where the cosmogenic radionuclide silicon-32 can be used. And so again, we have material which we, in a model, we can say is generated here. And if it moves along the coastline, just from a source region here, without any entrainment, downstream, we can expect one pattern of radio chemical activity changes as it moves from here to there, and decay takes place. And if it's receiving material all along the way, we can expect another pattern. So I'm not going to go into these equations, but they represent a advective type model of material from a source region here along the coastline progressively here, with decay of a radionuclide that's sourced here in the delta, and you can measure it along this pattern. If it's not replenished by entrainment of material from offshore, the radionuclide will decay and become lower. And so here are silicon-32 activity patterns along the Amazon dispersal system, with the Amazon delta, proximal delta here, the French Guiana coastline about here, about 700, 600, 700 kilometers downstream. And Shoily Rahman measured the lead-210, the silicon-32 activity here and here. And what you can see is if there were no introduction of new biogenic silica carrying silicon-32 into the system, we would have seen a simple decay away of the silicon-32 as it moved along the coast laterally toward the Orinoco. But in fact, you see extremely high silicon-32 along the Amazon, along the French Guiana coast, telling you that there's entrainment all along the way of new biogenic reactive opaline silica to sustain this kind of activity. So this is one example then of this entrainment that occurs using a totally different tracer than the lead-210. And I wanted to emphasize, because this group is particularly interested in carbon, that all of that entrainment involves carbon moving back to the shoreline where it's then remineralized. Now, in the last part of this talk, I'm going to talk about Papua New Guinea, which is an incredible place in terms of river inputs to the ocean and delta formation. There's a whole range of different rivers that surround Papua New Guinea. So this is a high relief system, high delivery, mountainous region that supplies tremendous amounts of material to the sea. And if you sum all these arrows, which is another one of these unidirectional Milliman type diagram showing the amount of metric tons, millions of metric tons of sediment brought to the ocean in the different regions of Papua New Guinea. If you go all around the island here, or the mini continent, I suppose, of Papua New Guinea and New Guinea, it's about equal to about 1.5 Amazons. So the integrated amount of material coming off this area is greater than the Amazon River. Now, I'm going to talk about this area right here and illustrate some of the processes I've tried to talk about earlier with the Amazon, and show that they occur here as well in the Gulf of Papua. So here's a blow up of the Gulf of Papua. There are multiple rivers entering the Gulf of Papua. The Fly River and the Parari rivers are the two largest. The Fly is on the, here you can see that the Fly River mouth, this kind of funnel shape, shows you the tides are high here, and the lack of funnel shape morphology off the Parari show you that the tides are lower on this sides of the Gulf. Now, one of the things that characterizes the Gulf is that all these river systems supply material which blends together to form a prograding cliniform delta out through the Gulf. So here are bathymetric patterns from the inshore, offshore, along this G transect here, and another one along the H transect here. And I'm going to show you data from different stations up on the inner shelf here in less than 20 meters of water, in 5, 8, 15, 14 meters of water, and a couple from 50 and 48 meters along this delta. Just to convince you this is a prograding cliniform, here is a seismic profile across the Gulf of Papua shelf in the middle here, essentially along between the G and H transects that I just showed you. Here's about 20 meters of water here going into deep water. And so you can see this classic type of cliniform structure with foreset and bottom set beds and top set beds here. And if you look functionally at how this system works, we have river inputs here on the left, mangrove coastlines here, sandy sediments, which I'm not talking about today, which accumulate inshore, and then movement of material out onto the top set, and then a further movement of material where it largely accumulates in that foreset beds of that cliniform structure. But what I want to talk, and so again, we're going to be thinking about this as material moving from land to the cliniform deposits, and then to the eventual bottom set and foreset deposits here offshore. And we have these vectors showing the direction of net transport of sediment. But I want to concentrate on these arrows going back onto this system that bring back into this top set region where we have mobile beds, some of the material that's formed offshore. So here's a cross-section, an idealized cross-section of this kind of system with mobile top set beds here, shown schematically, and shown schematically here with that kind of lead 210 mixed layer, fluid mud, overlying unconformably, slowly accumulating sediments here. We have bioturbidic sediments in the foreset region and mangrove deposits here. These are X-radiographs across this kind of system showing you the sedimentary structures that you see associated with these different depositional regimes. You can see this is 40 centimeters depth in the sediment, 80 at a site in the Pi Inlet, and 10 meters of water. Here we have 8 meters of water, and along that GH transect from the sediment water interface to 40 centimeters depth in the sediment. And both these sites you can see are highly laminated, showing you physical dominance of the processes that control sediment deposition. As you get into deeper water, you pick up biogenic structures in the sediment. Here again, this is 30 centimeters, 60 centimeters here, and 60 and 90 centimeters here in this should say 50, GH 50 meters of water depth. And so you can see that's translation from physically controlled depositional regimes to biologically mixed and reworked deposits here offshore. Now, one of the things that characterizes this system is that there's a huge seasonal variability in the wind, with monsoon winds going offshore and trade winds going onshore seasonally. And these southeast trades kick up the sediment, mix the sediment, move the sediment shoreward in this system. Extremely high winds. It's very difficult to work in the Gulf during the southeast trades because sustained wind speeds are 20, 25 knots are typical. So if you look at the color of the sediment in a 14-meter site in the middle of the Gulf here on the top set, this shows you the consequences of the wind-driven wave and tidal activity in the remobilization of the sediment. So this is a core that's exactly the same actually as the X-radiograph you were just looking at from, it wasn't exactly the same scaling as the X-rated graphs you were just seeing. Here's an unconformity. Here's a mixed layer in this deposit here. And this shows you the lead-210 reworked layer at this particular site's about 30 to 40 centimeters thick. And it's taken, this particular core was taken during the Southeast trades. Now, if you look at the thorium-234 in that core that you were just looking at, you can see that there's very high thorium-234 in it, penetrating to about 8 to 10 centimeters depth. That's during the Southeast trades. And the inventory during that time of the thorium is 4.8 DPM per centimeter squared. Here's the inventory and the profile during the monsoon when the sediment has been sitting there, unreworked are relatively stable. It accumulates a much lower amount of thorium inventory, about 1 DPM per centimeter squared, and its penetration is just a couple of centimeters. So what happens when the sediment sits there after it's been reworked during, for example, in this case by the trade winds, is the sediment goes through a transition of diagenetic redox reactions and becomes stuck for long periods of time in iron-reducing stages of diagenetic redox succession. And so the pore water patterns of dissolved iron that correspond to the 2 seasons I was just showing you at this site look like this. During the Southeast trades, when the sediment has been kicked up and oxidized, there's very little ferrous iron in the solid relative to the total reactive iron in the solid. Maybe 10 to 20% of the iron's reduced in that light colored layer you were just looking at. At the same time, there's very little iron in the pore water. This is the dissolved iron in the pore water. Now, if the sediment sits there for a while, the iron gets reduced. And so after a number of months, there's a lot more ferrous iron in that sediment. And there's much greater percentage of ferrous iron in the sediment before it's reworked and presumably reoxidized during the next cycle of trade winds. And during that time when it's sitting there, pore water iron grows in to much higher levels. And the change in the ferrous iron composition from here to here would correspond to a CO2 or DIC flux from the bottom of this system of about 30 to 45 millimoles per meter squared per day. So in other words, it's really reactive sediment. Now, if we look at these thorium-234 excess patterns in the Gulf as a function of the ratio of excess inventory to what you would expect based on water depth and a one-dimensional deposition of thorium-234, which is shown here by these dashed lines, if you look at the amount of thorium versus water depth here across the shelf that I've just been showing you, it's clearly a lot of excess thorium-234 is accumulating inshore, particularly during the trades, and then during the monsoon, where we only have one site here to compare with on this graph, there's much less accumulation. So the point is, during the trades, there's movement in particular of thorium-234 onshore, and it's plastered inshore during the trades and entrained into the bottom sediments during that time. And when that happens, there's oxygen exposure of the sediment, it's reoxidized. There's metabolite exchange of the sediment, as it's as shown earlier by that radium data from the Amazon shelf. And there's entrainment of reactive carbon, which enhances positive priming in the sediment. Now, the lead-210 profiles, excess lead-210 in this Gulf of Papua show the same thing. Here is the 0 to 10 meter bathymetric depth, 10 to 20, 20 to 30, 30 to 50. And this is the inventory of lead-210 here that we see in the sediment in the Gulf of Papua at multiple stations. This is the number of stations that each one of these bars corresponds to in these different bathymetric ranges. And this dash line here shows you the amount of lead-210 you'd expect if it just atmospheric input of lead-210 to this system. So there's a lot more lead-210 here, as we also saw on the Amazon shelf than you would expect based on atmospheric input. And I can't go through, and I won't go through the calculation here, but I followed a similar thing that Dave DeMaster has done on the Amazon shelf and the Mekong. And these lead-210 inventories must be accounted for by about 10 to 12 times the river flux of water from offshore into the Gulf of Papua. So there's a huge flux of water and particles, as shown by the reactive thorium-234, from offshore to inshore in this system. If we look in the sediment at remineralization of carbon in these sediments in the Gulf of Papua, and we plot the sedimentary carbon isotope composition of the organic carbon in the solid, shown here, on the del C13 value of that carbon and the del 14C value of that carbon, we get patterns of the solid sediment like this. If we look in the pore water at what's actually being remineralized, we get much heavier carbon in the DIC than in the solid carbon pool, and much younger carbon. And this reflects that entrainment of reactive carbon from the ocean, from the offshore regions, inshore into the Gulf of Papua, and it's blended with the older carbon, the more terrestrial carbon brought from the land, and then diagenetically remineralized preferentially so that we get a diagenetic fractionation of the carbon in the sediment. So I'm just going to summarize here. I know I've gone rapidly here and I've shown two different systems, but I've tried to emphasize today the fact that we have tracers available to us that can help us quantify phenomena like the onshore flux and entrainment of reactive carbon, that we can use these tracers to give us timescales and to demonstrate processes such as diagenetic fractionation of material brought from offshore, inshore, and we can also use these tracers like radium, for instance, to show the offshore export of diagenetic products like remineralized nutrients. And so this is a series of sort of summary of all the things I've mixed up here in my presentation, but I hope you'll take away that these are really complex four-dimensional systems. They're time-dependent, the three-dimensional in terms of material movement and onshore, offshore movement of material. It's not just a progressive movement of material from the land to the sea and the piling up of that material in big deltaic deposits offshore. There's a lot of interactions with the ocean, and we can quantify them with these suites of tracers that I've tried to give you some examples of today. So I'll end it there. I guess since I started 10 minutes late, I'm not too badly over time, but I'm a little longer than I intended to be. But I hope you take away the main points I was trying to get across here, despite my fumbling around a bit. So that's it.
Thanks, Bob. That was great. Let's open it up for questions. So people can either raise your hand if you have questions and we'll unmute you, or you can put questions in the chat. I also just real quickly I forgot at the beginning to say, while people are getting their questions together, I want to remind people that we will, the Leaky Deltas group will be having a workshop in March 2025 in Baton Rouge. And so if you are interested in talking about carbon on deltas, I encourage you to sign up. And Heather just put the link in the chat to express interest in it if you want to be kept in the loop. And with that, questions?
I should add that they're leaky both ways. If you take a bottom line here, they're leaky in all directions. Inshore,
sure, yeah.
Offshore, alongshore.
I have a question. I can start us off if no one's raising their hands yet while people are thinking. So I had a question about when you're talking about integrated oxygen exposure times, and I think I might have missed it in the last couple slides. Um, do you have a way to estimate oxygen exposure time, or more like relative oxygen exposure time, like for some particles get more compared to others? Or how are you estimating oxygen exposure time?
Yeah, that's a really great question. And the fact of the matter is we can only estimate oxygen exposure time sort of in a minimal sense. That is, we can only classically it was originally quantified using local diagenetic models and looking at the gradient of oxygen at one site into the sediment and determining how long material was in the oxic zone of sediments before it was buried, at least for the first time buried. And then subsequently, people began to try to incorporate the fact that particles don't just land one place and get buried there, but they move continuously into the ocean. So they're resuspended and re-exposed to oxygen many, many times. And in the case of the let's just say the Amazon, the way you might estimate oxygen exposure time would be the time that particles have been in transit along the coast. And so that might be, if you go from the Amazon to the Orinoco, it's about 1,000 years to do that. So that material is going over and over again. It's getting buried, reduced, and then it's getting exhumed and moved into the mobile outer part of this stream of mud and moved downshore. And so the minimum oxygen exposure time would be about 1,000 years, but actually it's even longer than that. It's going to be part of the time that it's plastered onto the shoreline, and then part of the time where it's moved offshore and then back onshore. So we can really only sort of quantify minimal estimates of oxygen exposure time. And but what we know is the sedimentary dynamics greatly enhances oxygen exposure time. And that example I gave from the Gulf of Papua illustrates that, where you have material sitting at a site, reducing, and then the trade wind forcing of the bottom currents and wave interaction with the bottom remobilizes that sediment, re-exposes it to oxygen, and essentially it's been, in a year, it's experienced another multiple periods of time of oxygen exposure. So the point is, it's just not a one-way street. It's back and forth, just like my talk here. So
No, yeah. Joe Tamborski has a question, and let's see if he can, and thanks for your answer, Bob. I appreciated it. Let's see, I think he can talk now.
Hey, Bob, can you hear me?
I can.
Great talk. Thanks for sharing. I'm curious if you were to go back to the Milliman diagram of all the vectors from the continents to the ocean. You've kind of made the case that there's the dissolved transport offshore, but there's this onshore transport of particles, right? So, thinking about this globally for global biogeochemical cycles, how might you suggest we start to tackle these issues as a community and thinking more about parsing out this inshore versus offshore exchange of materials?
Yes, I think the first thing I think we need to think of is that these are interactive systems, and we need to quantify those interactions using multiple tools on different timescales. And I just gave one sort of subset of the tools, emphasizing the thorium-uranium series tools that are available to us, in addition to that cosmogenic nuclide that Shoyle specializes in, and the silicon-32. And all of these have different timescales. All of them have different means of illustrating interactions. So, for example, the radium's a great way of showing fluid and dissolved solute interactions with solids in different areas. The thorium-234 is a great way of illustrating reactive particle transport that's associated with highly reactive, newly formed organic matter in the system and where it ends up in a given system. And the lead-210 integrates over much longer timescales, and but shows you sort of the mean behavior of a system on decadal types of timescales. And so, well, I guess what I would say is we need to go into different systems with these sets of tools and not just say concentrate on measuring only carbon components of the system. You need to use these tools in tandem with the carbon measurements in order to get the most out of how you can interpret carbon behavior in these coastal systems. So I guess I would say we need to take a multidisciplinary approach, and in this case, in the disciplines of biogeochemistry, not just the carbon group, but the radiochemical group need to join together with the sedimentology groups to properly constrain each of these systems, which will differ.
Great.
Does that answer your question in a long-winded way?
Yeah, it does. Thank you.
And what a great motivation for Leaky Deltas. We have a question in the Q&A. It's from Linquan Mew, and I'll read it to you if that's okay, Bob.
Yeah.
So great talk. I'm new to radioisotopes, but could you elaborate, for example, on how from the 234 thorium or lead-210 profiles, we can draw conclusions that the sediments came from offshore advected onshore instead of the other way around in the Gulf of Papua?
Yes. I'll try to explain. So here is a schematic diagram showing you exactly how I told you not to view a system, which is, but it's one way we can view it to help us understand some of the things, the controlling processes. So if you're in shallow water, here's a coastline, you're in shallow water, it might have low salinity, it might have high salinity, but uranium-238, which is the parent for thorium-234, is present in the water column in proportion to salinity and also water depth. So if we pick, let's say here, if I make you dizzy with this laser pointer, if you pick this water depth here, there's a certain depth of uranium overlying this square centimeter or square meter of bottom. There's a depth, every 10 meters of water depth is going to supply 1 liter of uranium-234 to every square centimeter of bottom area. So if we have uranium-238 decay to thorium-234 in the water column, and the particles on which the thorium-234 attaches to, it's a highly reactive nuclide, it attaches to particles. If they just went straight down from where they were attached to those particles, we'd accumulate an inventory underneath this water depth that's proportional to that water depth and the amount of uranium in it. But what I was trying to show you is that when we look at the distribution of thorium, which has to be formed here in abundance because that's where the uranium is, if we look at the amount in the sediment, we don't see the small amount of thorium here that we might expect that the thorium only came from here. We see a lot more thorium accumulating here than we would expect on that basis. And it must come from here, and it must move from where it's formed, where the uranium is, where the salinity is, where the water depth is, offshore. It must move onshore and accumulate there. Now, that doesn't mean you have net sedimentation, although you can. It just means you've exchanged the particles that were here with the particles that were here. And the sediment-water interface could stay at exactly the same position, but the particles that were originally here have moved up and out, and the particles that were originally here have moved in and down. And so that's where the inventory tells you, since it must form here, that's its source, but it ends up here, it has to be movement onshore and entrainment into the bottom sediments to be buried there. Okay, I hope that answers that question. And the same rule would apply to lead-210 as well, but in a different way, because lead-210 is sourced from the atmosphere from radon-222 and from radium-226 in the water column offshore. So I hope that gives you at least a qualitative sense of how you can use inventory buildup patterns related to where something has to come from to show you that it's not just one-dimensional, that it's a multi-dimensional exchange of particles from one place to another. And I didn't spend much time, in fact, I spent only one slide showing you that thorium-234 attaches to, because of its half-life, it attaches to labile material, typically planktonic material offshore, and that tracks the reactive carbon pool as it moves inshore. So where the thorium inventory is high, the carbon reactive inventory is inevitably high as well. This is the exact same thing that people use to estimate primary production in the open ocean using thorium-234 and sediment traps. That they use the ratio of thorium-234 excess in plankton accumulating in sediment traps offshore to tell you how much plankton export there was from a surface water region into the sediment trap that you're looking at. And that's a really a one-dimensional use of that tracer, and I'm using it in a multi-dimensional use using the inventory. Does that answer your question?
So they wrote in the Q&A, yes, it does. Thank you.
Good.
Yeah, no, that was a great explanation. I have a follow-up question, sort of, or Shirley, do you want to go first? I already asked a question.
No, if you have a follow-up, please go ahead.
Well, it's actually not a follow-up. It's follow-up to Joe's question a bit.
Oh, me too. So you go
Go
first.
for it. I already asked. I can follow up.
So Bob, can you all hear me okay?
You're a little echoey, talk slowly.
Okay. Bob, what's your opinion about the contribution of groundwater discharge to regions like French Guiana, where you do have those exposures of, in the erosional edge of the mud banks, where you will have exposure of a lot of sandy permeable sediment that then has some connectivity offshore. Have you thought about that, or do you have an opinion about what relative contribution might be?
No, I don't know. And I don't think anybody knows for that system.
Okay.
And that, that's one of the holes in our knowledge of these coastal systems is the groundwater inputs. And that's, again, where these radionuclide tracers, in particular the radium isotopes, can provide, really good insight into what these inputs must be. And so the radium, I was interpreting it the way Billy Moore did in that earlier work, that a lot of that radium-224 in that system of the Amazon has to come from remobilization of the bottom sediments and not likely from groundwater in that system, although there's certainly some groundwater input through the sandy areas of the Amazon mouth. And in the Gulf of Papua, there must be some from the sandy. There's extensive sand deposits in the inner Gulf of Papua that I didn't talk about. And they almost certainly represent sources of groundwater input.
Mm-hmm.
Now, I don't think that would affect the lead-210 in the way I was looking at it in those areas, although, you could have a lot of radium-226 coming in there, and and if it sat there in those areas and decayed in those areas long enough, you could affect the lead-210. But generally speaking, we ignore that contribution for that particular nuclide. But yeah, that's a great question. That's a wide open area. It certainly has feedback on carbon cycling by nutrient inputs that would not otherwise be there. It's another complexity that I think when you go into a system, you need to have that in your toolbox of how you are going to address nutrient cycling and elemental cycling generally in a coastal area. So I'm trying to open up the way we go and attack studying a system, you know. If you go in saying I can do an inshore offshore transect and nail down everything, you're liable to be way off.
Right.
You know, you've got to think of things 3 and 4 dimensionally.
Yep, it sounds like you're suggesting another very large project like Amasets to go to some of these systems, which I appreciate. Thank you.
For you and this group. Obviously, I won't be involved at my
You
stage.
never know, Bob.
Yeah.
Thanks.
I'll go ahead and ask a question. So I was curious, so building on Joe's question, these are 2 deltas. The Amazon is a very large, somewhat end member of a delta. And so I was curious if you've thought about to what extent this might be occurring in other regions, and like what other end members. It seems like if you were trying to make like some sort of categorical diagram or thinking of end members, you might have the Amazon on one end, but then you also might have that could categorize systems by like how much, if you're thinking about carbon budgets, like how much productivity is happening offshore that has the potential to be brought in, and then also something about like the physical oceanography that can actually bring this carbon inshore. Are there, I don't know, other things you might think about? I mean, about extrapolating some of the results here to other systems, or thinking about how to categorize this?
Yeah. So it's quite clear that not every system behaves the same, and certainly not the same as the Amazon or even the Gulf of Papua cliniform complex that I was talking about. So just to go back, sorry about this. So if you look at these numbers here, you can see the Gulf of Papua is about, that's of order of the Mississippi or bigger in terms of the amount of material that's brought in here. So that's an important single system. But how do these other systems, even around this single island, behave? There's no broad shelf here to bring in lots of water across the shelf on this North Shore area of Papua New Guinea. So that around this single island, there's a huge range of different types of systems that one could go in and probably see very different kinds of results from what I was showing you now. Now, the balance that I came up with for this using lead 210 is similar to what DeMaster and others got for the Amazon in terms of about 10 to 12 times the river flow into this area. But DeMaster's also done the same kind of balance for the Mekong Delta. And there it's only about 2 times the Mekong water flow that they were able to come up with. So it's quite clear that the entrainment of water off different systems can vary substantially. It's not always going to be 10 times or 5 times. It might be much smaller. And so I think 10 is about what you'd expect in an estuary generally. So these systems kind of behave like estuaries in many ways. And so when it has a nicely expressed estuarine physical oceanography, basically, then the salt balance gives you this kind of factor of 10, shoreward flow versus offshore. And so
yeah, no, I agree. A lot of your talk made me think of estuaries, because even like within an estuary, even if it's an estuarine source of carbon, if it's formed in a surface layer and sinking and then gets advected just further up the estuary, even if it's not technically an offshore source. So
right.
Anyways, thanks. Any other questions? Okay.
I have one. I have one.
Go for it.
Well, I have 2. I just wanted to query you, Bob, and the rest of the community or the attendees that are left. The first is, to follow up on Julia's question, is there an end member location that you think we should perhaps focus on to fill in a gap between this, was it this low yield passive margin versus what you focused on, this high yield? Well, I guess the active margin would be on the north side of Papua New Guinea. Is there another system? I mean, the one that comes to mind would be Bay of Bengal, but is there another one that you think?
Could you, for some reason, I'm having a really tough time hearing you.
I think I can paraphrase.
Yeah,
The question was, is there a more of a specific system you'd recommend as an end member? And sorry, I was trying to like do some logistics for the seminar, so I didn't actually hear all the question, but it was about any specific recommendations for an end member study site. Is that fair, Shoily?
That's right.
And thinking about yeah, but and then I think there's also part of the question was then also maybe like just within Papua New Guinea, you could use different sites as different end members.
well, Papua New Guinea is a great place to find multiple different kinds of end members, if you will, because as you go around this island, you find, you know, essentially active margin types versus passive margin type of broad shelf, very narrow shelf here up on the north coast. And here you can, the Arafara shelf sea is a carbonate rich sea. So here you have rivers emptying into a carbonate platform kind of environment. So that might be a great lower Paleozoic type of model system to go after. So I'm a big fan of this this place in the world as to pick different parts of it to study and compare as multiple end members. So that's a good one. There's only a few places in the world that haven't been drastically modified by people in terms of water balances and sediment balances. And one that Steve Keel and others have been studying recently is the Irrawaddy system. It's the last system in Asia that hasn't been extensively dammed. It will be dammed in the next 5 years or so. Even more than it has a few small dams on it now, but I guess it will be dammed in the way that the Changjiang is dammed, by the Three Gorges type dam, which completely alters these coastal sedimentary processes from what they were. So yeah, there's I would go around and this is a great place because it's not dammed. So that's one thing that I think of. If you want a system that gives you some insight into how things behaved in geologic time, you need to go to places that haven't been totally modified by people. And that's hard to find these days, as I just alluded to. And in Asia, you know, the last one standing is the Irrawaddy Thalwine system. And so
Thank you.
I don't know.
Okay. I want to acknowledge that we're over time, and so we understand if you have to go. Thanks, Heather, for reminding us. Is it okay if I still ask your question?
Sure.
With the acknowledgement that some people might have to go? Okay. Or do you want it answered offline?
Bob,
I'll
you're
do
welcome
whatever
to.
you want.
Okay. So in the chat, Heather put a question. So you bring a tremendous toolbox of tracers and other observing approaches for studying these systems. Working with hydrodynamic and sediment transport models seems like a promising way to get at physical entrainment and transport of particles on and offshore. What is the best way to collaborate with modelers, especially as we consider the interactions we want to foster at the upcoming Leaky Deltas workshop?
Yeah. So I'll go back to the Irrawaddy system, which I just mentioned. And that's an example where there's been a really good interaction between people like Courtney Harris, who specializes in physical oceanographic modeling and sediment transport modeling, coupled to marine geology and sedimentology observations by Steve Keel and others in the same system. And so I think having people like her, who are really amenable to interacting with crazy biogeochemist types, that's or sedimentologists, that's what you need. You need people that like working with each other and are interested in what each other brings to a problem, and in solving and that is realizing greater understanding and quantification and predictability in these systems. And so I would say invite people like Courtney to participate in these workshops, and some of it's pretty amazing.
Yeah.
What they come up with. Numerical modeling is really, it's great at producing things that look incredibly realistic, even if they're not realistic. But it's a wonderful way of quantifying these things, and used together in tandem with the observations, really powerful. Is that okay, Heather?
Thanks, Bob. Really appreciate that. Looks like you got one more question here. If you want to allow Jen to unmute herself and ask that.
Yeah.
Go ahead, Jen.
I am unmuted. I had a question in the Q&A because my chat's disabled, but I think Heather's question covered it. So,
Okay.
thank you.
I think there's one more.
Yeah. I just reopened the Q&A again. So there's one from Liviu Gyosan. How about systems off the Andes? Closer and less dangerous nowadays, most not dammed yet.
Well, could you repeat that, please?
Yeah. So the question was about, I'm going to put some words in their mouth. Maybe like the systems off of the Andes would also be good systems to consider working on. They might be closer and less dangerous now in present day, and most aren't dammed yet.
Off the Andes. So on the west coast of South America, is that what we're?
I believe so.
Yeah. Of course, there's been a lot of work in the upwelling boundary of that area. I'm not aware of any major river work. There's been, in terms of active small mountainous river work, there's been a
Hi,
lot
Bob.
of work on.
Oh.
Yeah.
Hi, Bob.
ahead.
This is Leo. Nice to see you.
Hey, I can't see you. I can only see your name printed out.
I'm not sure if I'm allowed. Or I don't know how to use it.
There were some security issues with some previous seminars, not ours,
So
but others.
my name is Liviu Gyosan. Just for future reference.
Thank you.
Nice to see you, Bob. I'm thinking about rivers coming from Colombia, lots of rain coming down and building deltas that have been studied recently by Juan Restrepo, for example. Lots of deltas that are undiscovered, and they are not dammed. And Irrawaddy, I've been working on Irrawaddy just before the war started.
Yeah.
And Papua New Guinea is very far and very dangerous.
Yeah. Yeah, that actually, in my own case, I had tried to work in the Irrawaddy, but then the coup happened, and that was that. And so that is an issue there. You're exactly right. I'm really not familiar with the rivers that drain Colombia, so I think those are the kinds of things and points that you make that should be brought out, put on the table and discussed 5
Yes,
people?
yes. Yes.
And that's really great to know. I wasn't aware of that opportunity.
That's the role of the workshop.
That's right. Now, I would challenge you about the dangers of Papua New Guinea, because the once you get out of Port Moresby or Leh, out of the cities, it's actually quite safe to work in
That's
Papua
true,
New Guinea.
but you wouldn't challenge me of how far they are.
That's true. That's true.
Thank you to the workshop organizers. They're this really good series.
Thank you. And thank you for attending and bringing questions.
Thanks, Livia. And I wish I could see you. I can only see your written name. But
I have more white hair, so.
Any last questions? Okay, well, let's give a huge thank you again to Bob. I know that's not very satisfying when only one person is clapping. But thank you, a huge thank you for that great talk, and for the Q&A. Thank you to everyone for participating in the Q&A. With that, we'll see you at the next seminar, which I think is in the fall, or at the annual OCB meeting. And in the meantime, please sign up for the workshop, expressing interest in the workshop that will be in March.
Yes, please do fill out that form.
Yeah.
Thank you
Thank
for
you very
having
much.
me. Thank you for listening. Appreciate
Thank
it.
you.
It was great. Thank you.
Thank
Thanks,
you.
everyone.
Bye-bye.